All right, so we already did the limits of theta goes to 0, sine of theta over theta equals 1. We already did that proof. So we're going to prove the limit as theta goes to 0 of cosine of theta minus 1 over theta. So here's the proof of number 6. So if I'm starting off with the limit as theta goes to 0 of cosine of theta minus 1 over theta, a quick trick that we've done in the past is to multiply by a clever 1. So I'm going to do cosine of theta plus 1 over cosine of theta plus 1. Put that in parentheses for you. So that way you can see that we're actually multiplying by 1 here and making sure that we don't forget to use our distributive property. So in the numerator, distributing cosine theta to the cosine theta plus 1. So I get cosine squared theta plus cosine of theta essentially minus the cosine theta when I distribute the negative 1, and then negative 1 times that 1 is minus 1. So I really left with cosine squared theta minus 1. And underneath I have theta times cosine of theta plus 1. Make sure you put parentheses, otherwise the theta looks like it's only attached to the cosine. And then from here, we can look at the numerator. If you recall your Pythagorean identity, this numerator, cosine theta squared, cosine squared of theta minus 1 is the same thing as negative sine squared of theta. So that's our Pythagorean identity. Okay, and I just copy the rest. And then I'm going to separate my fraction here a little bit cleverly. So first thing is, because we're doing with limits, the negative sign can be pulled up to the front here, right? It's just a constant. And then on the inside, I'm still left with sine of theta divided by theta times another sine theta, because the numerators multiplied together will give you your sine squared of theta. And underneath you have cosine of theta plus 1 still. So I purposely wrote it in this way. I don't need the parentheses here technically. I think it's pretty clear already. Now that I have this situation, remember for limit laws, I can use the product limit law. So you have the limit of the first fraction times the limit of the second fraction. And for the very first part here, this one here is our limit law, not limit law, our special trig function number 5 that's labeled above. So we get that's equal to 1, so negative 1 here, times. Now if I plugged in theta, I get sine of 0 over cosine of 0 plus 1, and that's negative 1 times sine of 0 is 0, and cosine of 0 is 1, so 1 plus 1 at the bottom. So this fraction here is just 0, so you have negative 1 times 0, which is indeed just 0. There we have our finished proof for number 6. So let's do some examples. So this is example number 5, I believe. The limit as x goes to 0 of sine of 7x over 4x. So when I'm trying to solve this limit, again, plugging in 0 directly, you get sine of 0. Sorry, 7 times 0 is 0, so sine of 0 is 0. And then underneath 4 times 0 is 0, so you have 0 over 0. So here's our little trick using our special trig functions. I'm going to multiply by a clever 1 again. And I'm going to choose 7 over 7 in this time, because when I do that, I get this is equal to the limit as x approaches 0 of 7 over 4 times 7 sine of 7x over 7x. And I'm going to put parentheses around this entire thing so you know it's the limit of this entire thing still. And the purpose of this, remember, is that we needed to make sure that this part essentially matches with this part. So that's why I chose a 7. Okay, because if you relate it back to the top here, for number 5, the theta for your limit goes to 0, and the theta in sine is divided by the same theta underneath. So we made sure that that matched. Now that we have that, I can go ahead and think about the fact that if we essentially let theta, actually let me do this first. This is a constant times a function, so let's take out that constant in front of our limit. So we get this situation here. So it's equal to that. And then now let me write the comment here that if we let theta equal to the 7x, then we essentially have sine of theta over theta, right? For this part of the fraction. So once we let theta equal 7x, as x goes to 0, like the initial part here, we can see that theta should also go to 0, because think about x going to 0 7 times whatever. As x gets very small to 0, theta must be 0, right? So then moving forward, this statement is really equal to 7 over 4 times your limit as theta, because I'm replacing that information now. So our theta is definitely going to 0, of sine of theta over theta. And so then we have 7 over 4, and this special limit is just 1, equal to 1. So the answer is 7 over 4. Alright, next example, number 6. The limit as x approaches 0 of cotangent of x cotangent of x. Well, normally what we do is if I put in 0, cotangent of 0, remember, is like x over y on your unit circle. So I'm just going to imagine that real quick. This would be 1 comma 0, so x over y would be 1 over 0, so that's kind of undefined. So we can't just do direct substitution. But we do know a little bit about our trig functions. Cotangent of x is just cosine of x over sine of x. So then I guess I should put the x on top for clarity for right now, right? So we get that situation here, x times cosine of x over sine of x. Now, this is where I wanted to match my number 5 and number 6 equations above, so I'm going to multiply by clever 1 again, by multiplying the top by 1 over x divided by 1 over x on the bottom. So 1 over x times the top and 1 over x times the bottom. So notice that the stuff in green is just essentially 1. If it makes your life easier, you could imagine dividing the numerator by x and dividing the bottom by x. That way, you can see that the limit, as when x approaches 0, x times 1 over x is 1, leaving you with a cosine of x on top, and underneath, sine of x times 1 over sine of x on the bottom is sine of x over x, like that. I kind of drew a big line here because, you know, it's divided by the entire thing. And so now when I take the limit of my rational function, essentially, the limit can be on the top over the limits on the bottom. And so notice how the bottom part is exactly like the setup of my equation number 5 above. So this is essentially equal to the limit as x approaches 0 of cosine of x. Well, that's just cosine of 0 with direct substitution. And underneath, using our limit law from above, limit as x goes to 0 of sine x over x is just 1. And so what's cosine of 0? That is 1. So 1 over 1 is just 1. And our very last question, to do a quick practice, is if you notice, we've been focused on essentially the number 5 equation and utilizing that. But so we should at least hopefully have a problem of that involves the other version, number 6. So let's do the limit as theta goes to 0 of cosine of theta minus 1 over cosine over sine of theta. And then to make it match any of these, notice how the top is already set up cosine theta minus 1 matches essentially the number 6. All I need is divided by the theta. That's what your variable is going to in your limit, right? It has to all match there. So notice that I could just multiply the top part by 1 over theta and the bottom part by 1 over theta, so now I have a clever 1 again. So this is equal to the limit as theta goes to 0 of cosine of theta minus 1 divided by theta, that's on the top. I'm going to draw a big line here, so that's divided by the sine theta that was initially there. And then sine of theta times that 1 over sine theta in the denominator will leave you sine theta over theta. And let me erase this so that you can clearly see that this limit is in front of the entire fraction right now. And so now, using our limit property laws, I could take the limit as theta goes to 0 of the numerator over the limit as theta goes to 0 of the denominator. And what is cosine of theta minus 1 over theta as theta, the limit as theta goes to 0? Well, that is essentially number 6, which said it was 0, right? And then over here, in the denominator, the limit as theta goes to 0 sine theta over theta is 1, so 0 over 1 is just 0.